10% impurity elements, and mainly they are iron, so 10%, and some other minerals or gangues. So if we are analyzing the separation of zinc concentrate, we can find out that the most important part will be sulfur, and the second one will be iron. And besides iron and sulfur, in the gangue path should be separated as well. So besides the separation of those impurities, there are some special elements that we should pay attention to. The first one, we are talking about lead. So lead content is around 1%, and along with the depletion of high quality resources, the lead concentrate in the lead content in zinc concentrate are increasing dramatically nowadays. So it can be several percent. And besides lead, the cadmium, so it's a very, how to say, typical toxic elements in zinc process, and it can result several, how to say, serious disease for human beings. And it also can be used, can be recycled as a byproduct. And copper is a similar work, is a similar element. It can be recycled, and as I have mentioned, the copper content can be 0.4%, and high mercury and arsenic, so they are toxic elements, and they should be well monitored in the process of zinc. And besides those toxic ones, one precious metal, silver, so it's quite high in zinc concentrate. And tomorrow we are going to study lead smelting process. We can find out that in lead concentrate, the silver concentration or silver contents are even higher than that in zinc process. So we can make a conclusion that the zinc can be, how to say, has a smaller assignments for separation, and the concentrate contain lead, cadmium, copper, toxic elements, and precious elements. So in the extraction process of zinc, we should try to figure out the reaction behaviors of those elements or those components. Because of the twins, these two twins, zinc and lead, the core smelting of lead and zinc are commonly, organized all over the world. So in the second part, we will try to study the extraction flow sheet of zinc step by step. So as I put in this title, the roasting, leaching, iron removal, purification, electrical refining. So these 5 steps are widely used in zinc smelters or hydrometallurgical process of zinc all over the world. And if we are counting the yield of different technologies for zinc production, we can find out that refined zinc can be produced from primary resources or from secondary resources. And nowadays, we have the preliminary numbers, like 90% of zinc are produced from primary resources, from zinc concentrate. And the secondary zinc, as I have mentioned, zinc has a close relationship with iron and steel. So when those iron and steel are recycled, the zinc will report to the flue dust phase. So the flue dust of the iron recycling process can be used for zinc production. And this part is increasing nowadays, not only in China, but also all over the world. And because the primary zinc production is still the main part, so we are mainly try to study or try to present this flow sheet for zinc production. And for primary zinc production, there are also 2 different different kind of technologies. The first one is hydrometallurgical process. So as I put in this title, so roasting, lynching, iron removal, purification, and electrical refining. And this account for 85% of zinc production. And also there are some small part, like 15% of zinc or primary zinc is produced from primary or from pyrometallurgical process, like ISP, impulse melting process, or electrical furnace technologies, and they can also produce zinc, but the amount is smaller than that from hydrometallurgical process. So we're usually talking about the production of zinc, and we are using hydrometallurgical process. And this is a typical main flow sheet for the zinc production. So the concentrate is mainly consisted of sulfurite, ZNS, zinc sulfide, and also there are some returns or reverts. They are going the roasting process, and the Cat9 they are going to the neutral lynching, and this spent electrolyte from the electrical veining process are used as a lynching solution. And then after the separation, the residues are processed with stronger acidic solutions to promote or to improve the lynching efficiency of zinc and other valuable metals from the residues. And after that, we can get some residues like lead and silver. And we know that in the hydrometallurgical process of zinc, we are using sulfuric acid. So in sulfuric acid, lead and silver, they are not dissolving into a solution, so they will remain in the residue or in the understream. So this residue or this slurry enriches lead and silver, and they can be used as materials for lead and silver recovery. And in the natural lynching process, we have got the solution. So zinc sulfate solution, it will go to the purification and electrical veining process. So the purification, electrical veining process, and this iron removal process has been used as here, like hematite precipitation. Hematite is a typical iron mineral which is used in zinc hydrometallurgical process to remove the iron in this solution. The solution from the hot acid lynching. And we will have detailed discussion in following slides. And this is a brief introduction of the flow sheet of zinc, which is widely used all over the world. And as I have mentioned, China has quite a large scales of zinc production industry. And this photo was taken actually 3 weeks ago. And in the middle of July. And this is my picture. And I have guided some 10 students in a zinc plant, zinc smelter. And here, this is the equipment for the roasting, and it's a fluid roasting furnace. It's quite one of the most important equipment in this smelter. And this is the fifth floor of the factory, and we have the bird view of this smelter. And I have some videos as I have mentioned, and probably you will be interested. So let's go. And as I have mentioned, so this is these are rubbers which are used for their cathode or the zinc, the product of zinc hydrometallurgical process. And after the electrical weaning process, this cathode, which is permanent cathode, and we have zinc deposit on this cathode. And when they get washed and dried, and they are moving to this auto blade system, and it can be blade into two pieces and get and we are wrapped for the following process. Probably one more time. So this is the product for the electrical weaning process. And this process, actually, I would like to, the purpose of sharing this video is that I want to tell you that electrical weaning and the following process are highly equipped with automatic machines, with robots and with some sensors, and not too much labor are needed nowadays. So they are zinc cathode or refined zinc. The purity is about 99.993 or 994, and those cathode zinc are sent for the alloy part or for casting part. It can be used for different purposes. And one of the most important form of this product is zinc ingot like this. So the color looks like silver, but this is zinc. This is zinc. So if we are going to check this process or this robot, you can find out that. So this is the robot arm, and those anode zinc are melt and cast and cooled down, and they can be moved in different or indeterminate weight. And this belt will move or will transfer those zinc ingot into next step. So in the next step, there's another auto drive machine or auto drive transfer machine, and they are moving those zinc ingot and try to deposit them into this store or into this factory, and it can be sent or can be sold out for different purpose. So with this sensor, and it will have very accurate location system. So after that, so it's changing and moving those ingots into this position, and the trucks can try to deliver those zinc ingots into different places. So this is a story after the electrical weaning process. And mainly we are going to start this four stages this afternoon. The first one, the most important, because this is an international virtual course on metallurgy. So we want to know the mechanism, or we want to know the chemical reactions between or behind this flow sheet. So the roasting, as I have mentioned, the facial center cubic crystal structure, zinc sulfide, sulfurite. So this should be transferred, or this should be processed, and we are needing only one element, zinc. So zinc should be separated from the rest of the elements in this table. So what should we do? As I have already mentioned, zinc has the largest concentration number in this concentrate, and besides zinc, one of the most important one, or the largest impurity element will be sulfur. So probably in this roasting part, I would like to determine, or I would like to see that in the roasting process, majority of the sulfur can be removed. And this process is designed for the separation of sulfur from the rest of these elements in this table. So what are the reactions happening, and what kind of equipment and chemical mechanism in this process? And we will go one by one. As I have already mentioned, the chemical composition of the zinc concentrate will be zinc sulfide, so ZNS, and we are needing zinc from the concentrate. So zinc should be separated from sulfur. And if we are checking the thermodynamics of the system, zinc, sulfur, and oxygen with HC or with theoretical calculation, we will find out that when we are decreasing the sulfur potential of the system, and when we are increasing the oxygen partial pressure and try to decreasing the sulfur partial pressure, we will find out that zinc sulfide will move to zinc oxide. And when we are increasing the temperature from 600 Kelvin degree or to 1200 Kelvin degree C, we'll find out that the A and B refers to the gas composition of industrial practice. We'll find out that when we are increasing temperature, this 2-point moves to the stable zone of zinc oxide. And if we are checking about the product after of the phase transfer of zinc sulfide, we can have different options. It can be zinc vapor, it can be zinc oxide, it can also be zinc sulfate. And if we want to get zinc oxide, the oxygen partial pressure is too low to be realized in industry. So properly, we are not using this part. And if we are going to zinc sulfate, and it can be achieved when we are processing zinc sulfide concentrate at low temperature. And this one can be easily lynched with water. And with this process, zinc will dissolve into the aqueous solution system. But with these reactions, the sulfate in the system will transfer into sulfate acid. As I have mentioned, in the electrical weaning process. Because in the electrical weaning process, zinc deposit in the cathode, and in the anode, oxygen will form, and H plus will form in the cathode as well, in anode as well. So these two will form the sulfate acid. So this one cannot be aggregate in the system, and this should be well monitored or should be balanced in this system. And another one is about the zinc oxide. When we have zinc oxide, it can be the best option for the roasting process, can be the best product of roasting process, because zinc oxide can be lynched with hydrogen, and we can get the zinc ions into the aqueous solution system. And when this one is electrical weaned, we can get acid again, and this acid can be returned to this part, And with this design, or with this circulation, we are producing the zinc in the electroweaning from the cathode. And the sulfur in this process, when we are producing zinc oxide, and the sulfur will move to the gas phase, it will transfer into sulfur dioxide. And with mature chemical technologies, sulfur dioxide can be easily transferred to sulfur trioxide. And when we are observing sulfur trioxide with water or with dilute sulfate acid, we can produce this chemical or very important commercial product, sulfate acid. So with this roasting process, we can make a conclusion. We are producing two important products. One is zinc oxide, and another one is sulfur dioxide. And zinc oxide will be used for following stages, and sulfur dioxide can be used for the production of commercial product of sulfate acid. So this is analysis of this chemical potential diagram of zinc, sulfur, and oxygen system. And besides zinc, sulfur, oxygen system, and this is a industrial practical parameters in zinc roasting, zinc sulfur concentrated roasting process. The sulfur dioxide concentration is around 10%, and the oxygen concentration in the gas phase is around 5%. So we are in this part. So the main product of zinc sulfide after the roasting process will be zinc oxide. So this is a terminal product for zinc sulfide in the roasting process. How about the others? The behaviors of impurities are also interesting, as we discussed in the starting material, or as we discussed for the raw material for zinc production, the zinc concentrate or the minerals. Copper is more expensive than zinc, and it mainly present as copper sulfide in the mineral or in the concentrate. So when we have the composition of the gas phase, so we know that the copper sulfide will transfer to oxide as well. But because copper has two different oxidation states, and the temperature is around 1000 degrees C, so there will be some part transferred to molar, just to +1, and some will transfer to +2, and this ratio varies from the oxygen particle pressure, and also varies from this temperature parameter. So we know that the copper will transfer or will become copper oxide in the Cag9 or in the product of roasting process. And the lead is a twin brother or twin sister for zinc, and under the processing parameter of roasting, we can find out that lead is easily transferred to the lead sulfate, because there are different forms of lead sulfate with different bases, with different chemical formulas. But when we are determining the composition of the gas phase, we know that the main form of lead product will be lead sulfate. So we have zinc as oxide, copper as oxide, and the lead as sulfate. So if you recall the flow sheet of zinc production, we usually product a set stream of lead silver residue. So it's a lynching residue of the Cag9, and the lead mainly stays in the form of lead sulfate. And besides the behavior of lead, copper, and zinc, the ganglion elements like silica oxide is also important when we are using this flow sheet. And there is a limitation, or this is a requirement. When the total amount of lead, copper, and quantity of silica oxide are higher than 5%, the roasting process will have large challenge, will have a lot of problems. And the reason is the formation of some liquids. So this is fully liquid regions. So in the binary system of lead oxide and silica, you can find usually we are using for 940 degrees C of the processing temperature. So with this temperature, we can find out that when we have large amount of lead and silica, we will have the possibility of liquid formation. And a similar story can be found between the binary system of lead oxide and iron oxide, and also the copper oxide and lead oxide. if we have silicon oxide, it will have also reactions with copper oxide. So when we are using the roasting temperature of 940 degrees C or even higher to 980 degrees C, so the formation of liquid will have larger amount, will be easier. So because we are producing some Tec-9 which can be easily for leaching process, so the amount of liquid should be well controlled, and formation of liquid is determined by those impurity components or impurity. So we have to make a limitation or requirement for those impurity elements. Besides iron, besides lead, silicon, and copper as impurity elements, the most important or one of the most important element will be iron in zinc production or in all non-ferrous metal production. So the reaction behavior of iron is an important topic, for us. And the formation, as we check the chemical potential diagram of iron, sulfur, and oxygen, if we are producing zinc oxide, so the form or the stable form of iron will be ferric oxide, and these two can form a spinel phase. We call it zinc ferrite, and which is ZNO, so which can be written as ZNO. So the spinel formula or structure. So when we have this roasting process, we will get a product called zinc ferrite, and this zinc ferrite causes a lot of problems for zinc hydrometallurgy. And if we are talking about the leaching, iron removal, purification, especially these two parts, and they are making efforts to solve the problem which is resulted by zinc ferrite, and we will have more discussion in following chapters, in following slides. And the formation mechanism of zinc ferrite is a good topic, an important topic for roasting. And a lot of researchers from different universities have done some work like the MTB in JLM, MTB, and a lot of people have done such work. And the conclusion is that the formation of zinc ferrite is cannot be ignored, or cannot be, the formation is a certain will happen or must happen or will happen in this process. Cannot be avoided. It's the right word. And if we have some detailed discussion about the Tec-9 or roasting process, the distribution of zinc ferrite, zinc oxide, and zinc sulfide in Tec-9 can be started. So this is a location of zinc, of iron, and this is the center. This is the center of the particles, and in the outer layer, we have enriched iron, and in the outer layer, we can find out that this zinc ferrite will make a coating layer, or will move to the outer layer of this Tec-9, and when it has a layer, and during the leaching process, the hydrogen ions cannot react with Tec-9 efficiently. And in the center we have iron. We have some sulfur and zinc. This is unreacted chlorine. When we have the information, or when we have the knowledge about the roasting process, we know the presenting form of the Tec-9. There is mainly consisted of zinc oxide, and some copper oxide, lead sulfate, and zinc ferrate. And there are also some gangue components and products of some other impurity elements. And those cation will be subjected to lynching process. As I have mentioned, the sulfate acid is used, and those oxide can be easily lynched. And zinc, copper, and some other cations, they can dissolve, or they have large solubility in aqueous solution. So after the lynching process, those treasures or precious metals, they are moved into the aqueous solution phase. Some gangue parts, some gangue components, or some cations which form insoluble compounds like lead, it will form lead sulfate. Calcium, it will form gypsum or calcium sulfate. They will report to the slurry or the lynching residue. And some part will dissolve into the solution phase, especially the oxide. So when we are starting the lynching behavior of oxides, so we can find out that we will have this ferric oxide, aluminum oxide as gangue components, zinc oxide, because this is main product of the cation. So this is the relationship between the concentration or the activity of those cations, like ferric, alumina, zinc, with the relationship was their activity and the pH value, like acidity. When we are going to the stronger acidity or acidic conditions or atmosphere, we can dissolve even ferric oxide. And when we have a 9 somewhere here, so when we have the pH value about 4 in the system, and there is some kind of 10 minus 0.01, if we are hypothesize the concentration with the value of the activity, we can find out that with this pH value, the alumina will stay as cations in the solution, and zinc will present as cations, and so there are some other elements. But the iron, it will present as precipitate or as lynching slurries. But if we are going to more acidic conditions, like the pH value is smaller than 0 or just equals to 0, we can find out that the ferric oxide will be lynched out. We will have ferric ions in the system. But if we are moving to more basic conditions like pH value of 7.5, the zinc oxide cannot be lynched out. So properly, the precision, we will find some appropriate pH value to get the target oxide to be lynched out, and try to leave some oxide in the lynching residue. So the cations in the solution will be sent for the following stages, and their behaviors in the aqueous solution phase is also an interesting topic, and we should have the knowledge about this. So as we discussed in the previous slide, so if we assume the concentration of different cations with the activity numbers, we can find out that when the activity is 0.1, we make a hypothesis. We find out that when we are increasing the pH value, so the first cation which will precipitate will be ferric ion, so it will going to be Fe3+. And if we are increasing higher, so the tin is going to be precipitate. But the others like aluminum, lead, copper, and those cations will still present as soluble ones. And in this diagram, we are not using, or we are not considering about the influence made by sulfate ions, and you can assume that this is in this system, so the lead can present as ions in the solution. And along with increase in the pH value of the system, alumina will precipitate, lead will precipitate, copper will precipitate, and ferrous ion will precipitate, and very closely, zinc will precipitate. So we have the idea that if we want to separate zinc from the cacnine, from the product of the roasting process, we should make sure that zinc oxide is lynched out. And more importantly, zinc ion in the aqueous solution should not precipitate. It should present as soluble ions. So we have to make such a value or such a decision. The pH value of the lynching solution, the terminal pH value of the lynching solution should be smaller than 6, according to this figure. When we are moving to this acidic position, zinc will present in the solution. If we are moving to this side, it will precipitate. So we have the nothing, and zinc still present a solid phase in the lynching story. And if we have the zinc as soluble ions, the copper, lead, alumina, tin, and iron, the behavior of those cations, they will vary as a relationship of pH value. If we are here, so only iron and tin precipitate. But if we are moving to this place, both iron, tin, alumina, lead will precipitate. So this is a very good textbook in controlling the pH value of the lynching solution. And if we are going further, so besides the pH value, and the potential of the solution is also important. The potential of the solution is also important because we would like to transfer zinc sulfide into zinc oxide in the roasting process, but there are some part of zinc sulfide remains in the cacnine, just like the unreacted shell, unreacted core. When it is not oxidized, the chemical composition is still zinc sulfide, just like in some place somewhere here. But when the potential changes, it can also be oxidized, and is the direct lynching of zinc sulfide. There are also some industrial practice. And if we check this pH value, potential pH diagram of zinc water system at 25 degrees C, we find out that we are determining at this region, and this is a formation of hydrogen, this is the formation of oxygen. So between these two lines, this is a stable zone of aqueous solution system. And when the pH value is smaller than this value, so we will have these soluble zinc ions, the pH value. So similar result with the previous one. So as I have mentioned, when we have some unreacted zinc sulfide, when we are decreasing the pH value and we are also increasing the potential of the system, it can also react with reaction 6 or reaction 1, and zinc can be soluble ones, and the sulfur can transfer into also sulfide ions or elemental sulfur. And these two reactions happening in a direct lynching process. And in the lynching process, we have the idea, or we have knowledge about the lynching pH value and potential of the cacnine, and there are also some other impurities in the system. So first, we have grouped we have grouped those impurities. Like group 1, we have lead, we have calcium, and magnesium. So these three elements, so they have one similar property. When they form some compound with sulfate acid ions. So when they form sulfate, those compound has very small solubility in the aqueous solution system. So majority or mostly they will enter into the slurry, the lynching residue, lynching slurry, and they will report to the lead and silver slurry. And the solubility of calcium sulfate and magnesium sulfate are very small in the solution system, but it still has some solubilities. So partially dissolved, but these dissolved ones will result several problems in industries, like they will precipitate in these channels or in those tubes, And when these tubes, when this diameter decrease along with the precipitation of sulfate, this process will be influenced. And if this kind of joint, when they blocked with sulfate precipitation, it will result serious problems. And they can dissolve slightly or partially into the solution. So we have to try to control or try to remove them into some parts. And this is solubility of calcium sulfate in the simulated solution phase. We can find out that when we are lowering down the temperature, we can find out that the solubility of calcium sulfate decreases a lot. So we have the idea that if we have a high calcium concentration in the solution, we can try to lower down the temperature of the solution phase, and calcium sulfate may precipitate from solution phase. And the concentration of magnesium cations in the solution phase, we can only be monitored by picking the concentrate. We have to use with some high quality concentrate with small magnesium content, and the discharge magnesium from the neutralization zinc in the waste electrolyte is another routine, and the solution should be treated to remove those magnesium. And another group 2 will be some elements which have high solubilities in the solution phase, like zinc, iron, cadmium, nickel, cobalt, and they will report to the solution phase. In the lynching part, the composition of the lynching solution of one smelter in China, we can find out that after the natural lynching, the zinc content in the solution can be 100 to 170 gram per liter. So when we have 1 liter lynching solution, we can recycle, or we can get around 170 gram of zinc deposited in the cathode in the electrical welding process. And besides this zinc, we have also some amount of copper cations, some cadmium, and some toxic arsenic, some critical elements and antimony, some energy metals, nickel and cobalt, some treasures, critical metals, germanium, and manganese, and calcium, and along with the increasing of the amount of secondary resources in the feeding materials, the halogens like fluoride and chloride in the raw materials are increasing, and the concentration of those elements are also increasing in the solution phase. So that's the composition of the lynching solution. And the group 3 will be some impurity elements like iron, arsenic, antimony, and germanium. Even germanium and antimony, they are precious metals, and they have very special property and important applications, but they have very bad and very negative influence with in the electrical weaning of zinc sulfate solution, and will make it will lower down the quality of the cathode, and will also decrease the lifetime of the electrolytes. So we have to control the concentration of those elements in the solution or in the electrolyte. But the good idea is that when we have those impurities in the system, and they can, part of them will report to the leaching slurry. But we have to make some efforts to use the properties of some ions. So for example, the ions, so like iron, ferrous iron should be oxidized to ferric iron, as we analyzed with the pH and log AMA diagram. We find out that when we want to have the iron, so this is a ferric iron, and the ferric oxide is somewhere here. So this is 2, and we have the ferrous iron, so 2 plus is here, and we have the ferrous oxide or OH2. So there are some difference between the precipitation of these 2 ions. So if we want to, and zinc is somewhere in the middle. So if we want to separate iron from zinc, the good idea is that we are oxidizing this ferrous iron into ferric iron, and will precipitate when zinc iron is stable. So in the leaching stage, the ferrous iron is oxidized to ferric iron, and we usually use some manganese oxide, so MnO2. So this one can be used as oxidation reagent to transfer or to convert ferrous to ferric. And when we have ferric in the solution and the pH value is controlled in the middle or is higher or larger than the precipitation or hydroprecipitation of ferric iron oxide, it will form this as ferrihydrate. And 5.2 is the isoelectrical point of this ferric hydrate. So it will have the highest precipitation or settling speed. The separation between iron and zinc can be realized partially. And along with the precipitation of ferric iron and the settling of the precipitate, some other impurity elements like arsenic and antimony, they can be simultaneously removed. They can co-precipitate, but the mole ratio of these 3 elements should be well controlled, and the mole amount of iron should be 10 times larger than the total of arsenic and antimony. And with this ratio, those 2 elements, 2 impurities can be co-removed with the precipitation of ferric iron. And germanium, as we mentioned, at the leaching conditions, they will generate some compound and call it and will report to the leaching slurry. And silica is another important and classical impurity element in the system. And under the leaching conditions, it was polymerized into silica acid and will colloid and into the leaching slurry. So this is the media leaching stage of the calcinine. So the natural lynching, so we can make some important remarks. So the final pH value of this natural lynching is 5.2 because this is the isoelectrical point of ferric iron oxide hydroprecipitate, and the lynching temperature is 50 degrees C. And in this natural lynching process, you have two important functions. The first one is lynching zinc into the solution, and the second one about the precipitation functions. The precipitation, it removes iron, it removes arsenic, antimony, silicon, and germanium. So those impurity elements will be separated from the solution, and those impurities report to the lynching residue. So with this single step, we have two functions. And during the lynching process, the acid in the lynching solution, which is usually spent electrolyte. So the acid in the spent electrolyte will be consumed. So the pH value will increase, but the terminal or final pH value should be controlled around 5.2. And the most important, one of the most important reactions will be the oxidation of ferric iron to ferrous iron to ferric iron with magnesium oxide. And the mole ratio of those impurities should be well controlled to get the co-precipitated. And germanium and silica will also partially report to the lynching slurry. So this is beauty, or this is wisdom or knowledge of this natural lynching process. But if we are checking the economic parameters in this lynching process, we find out that so the chemical composition of the low acid or natural lynching acid slurry, we find out that the total amount of zinc in the lynching slurry is about 20%. In the lynching slurry. So when we have 100 kilogram lynching slurry, 22 kilogram zinc are waste or are reported. 22 kilogram zinc reported to the slurry. And this 22 gram, they have different forms, mineral forms, compositions. And this zinc ferrite, this is the most important mineral in the lynching slurry. And there are also some iron-reacted zinc sulfide, and zinc silicate. They can have some minor amount. Zinc oxide, the iron-reacted cacnine, and zinc sulfate, which can be washed and which can be recycled by washing. And the major problem will be the lynching of, or will be resulted from zinc ferrite. A lot of famous researchers like Dimopoulos, like Filippo, they have studied the lynching and the formation and lynching of zinc ferrite in the zinc hydrometallurgy process. So let's make a remark. If we want to recycle higher amount of zinc oxide, we have to improve the lynching efficiency of zinc, or we should treat this low acid lynching slurry with another process. And within this lynching slurry, zinc ferrite is the most important target mineral. So we have a lot of engineers have developed another technology. The technology is called acidic lynching. So if we are looking at the parameters or the numbers after later lynching, those slurries can be treated with acidic lynching. The terminal acidity is 1 to 5%. So the pH value, if you are calculation, if you are calculating the pH value of the system with 5 gram sulfuric acid, you'll find out that the pH value equals to some amount of 2. 1 to 2 is the pH value. And in the natural lynching, the pH value is 5.2, around 5.2. So the acidity of the lynching solution has been improved or has been promoted, and temperature has been increased from 50 to 60 degrees C to 70 to 80 degrees C. So with this improvement, the lynching efficiency of zinc can be improved, especially those zinc ferrite can be improved. So with this two-stage lynching, the lynching efficiency of zinc can reach 85%, and previously the number is around 78. So we have 7% improved. And the lynched slurry still contains some 20% zinc, and 5% are soluble ones, can be improved by washing. And if we want to improve this number, 85%, we have to make more effort. But after this acid lynching, we can lynch 80% of the copper, cadmium into the solution, and also the cobalt and the energy metal can be lynched out. So after the acid lynching, hot acid lynching should be considered or has been developed. The temperature increased to 90% and 90 degrees C, like almost the boiling point at ambient atmosphere, and terminal acidity reached 20 to 60 gram per liter. So it's quite strong acid or acidic atmosphere. So the lynching residue can be well lynched out. But as you have realized, so the chemical formula of zinc ferrite is ZnO and Fe2O3. So if we have lynched this zinc out, and it will go to the solution phase, so does iron oxide. So large amount of iron, 3. So ferric iron, it will also move to the solution phase. And as I have mentioned, we should separate zinc from iron, and nowadays both zinc and iron, they move to the solution phase. So the separation of zinc and iron should be realized in the aqueous solution phase. So we have to think about the ion removal or ion separation from zinc in the solution phase, in the lynching solution phase. And in industry, there are some developed or some used technologies for ion removal, like geoside process, and drag geoxide process, hematite process, jemicide process. So these 3 minerals, and both 3 minerals contain certain amount of iron, and they can be used as the precipitant form of iron from the solution. So first of all, let's check in the lynching process. Besides this acid lynching, hot acid lynching, another very novel or quite smart process for the lynching of the lynching slurry from natural lynching is sulfur dioxide reductive lynching, which is developed by Ejima smelter in Akita in Japan. So this technology is used in Akita zinc smelter, and the lynching is realized with some autoclaves. So they are pressure kettles. So some liquid sulfur dioxide is injected, and the zinc ferrate reacted with acid and sulfur dioxide, and they form this zinc sulfate and ferrous ions and water. And if we directly use acid or hot acid lynching, we are producing zinc 2 plus, zinc ions, and the ferric ion. So 3 plus. And the difference between those lynching process will be the product, the form of ion. So here with SO2 or sulfur dioxide reductive lynching, we are producing ferrous ions. But if we are lynching directly with strong acid, we are producing ferric ions. So this is quite important difference. And it has strong influence with the following ion removal process. And if we are go to the equipment for lynching, so this is a mechanical stirred lynching tank. So the slurries with slurries like we have the concentrate CAC9, we have the CAC9, and we have the spent acid, and they are slurrized and injected into this tank, and this mechanical rotation, and there are material flow and strong lynching reaction happened here, and we can put some gases, and we can also put some additives like MnO2 try to oxidize the ferrous to ferric. So into this process, and the reacted slurry can be poured out and for separation. And this is widely used thickener. And this screw slowly rotates, and the solid particles or precipitations settle down and deposit at this underground. And with this rotation of screw and the solid parts will merge and get enriched into the understreams. And those clean or clean solution phase will flow from this pipe and go to the following process. So that's equipment for the lynching process. And this is the flow sheet with Jemosite method. So the concentrates, so the roaster, and this natural lynching. So after natural lynching, the solution go to the purification, and after purification, so the electrical refining, and we are getting this cassette zinc. But the underflow of natural lynching, there are 22% of zinc in the lynching slurry. So this lynching slurry get further lynched. So weak acid lynching, and get weak acid lynching. So the underground or understream go to a pressure or another lynching stage, and go to higher and higher. And in this weak acid lynching, this solution returned. And in those acid lynching or pressure acid lynching, the solution will have a very high content of ferric ion. So those ions should be separated with some method, and the ferric ion in the solution is treated with jarosite precipitation process. In this jarosite precipitation process, we are producing this solid waste, which contains certain amount, from 20 to 30% of iron in the solution, or in the residue. And with this way, some part of zinc can return with the lynchant. So this is an example of the flow sheet in industry. So as we mentioned, if we are aiming at recycling higher amount of zinc after natural lynching, we have to treat the natural lynching residue with some other techniques like acid lynching, hot acid lynching, or sulfur dioxide reductive lynching. With those processes, iron will report to the lynching solution together with zinc. So the separation of iron and zinc should be realized in the solution phase. And when we are going to separate the zinc of separate the iron from the solution phase, we have to find some knowledge, or we have to know the mechanism of iron removal. And in the solution phase, we have zinc ions, we have sulfate acid, and we have ferric or ferrous ions and some other ions. And the biggest part will be water. So in this aqueous solution phase, how to get this out? And we are checking the phase diagram of ferric sulfate acid and water system. And this is sulfate acid with excess. So along with, so we are moving to the right side, more acidic conditions. We will reach more acidic conditions. And this temperature, so we are moving from the ambient atmosphere to autoclaves, because when the temperature is higher than 100 degrees C, we have to use autoclaves. And this y-axis is about the ferric ion in the system. So you have the idea. So we are only mentioning about ferric ion. So the amount of ferrous ion, so Fe2. So this one is not how to say mentioned, or is not well controlled. And only one should be the ferric ion. It should be controlled. So in this 3-axis diagram, we find out that iron can precipitate as geosite, can be precipitated as hematite, can also be precipitated as copper siderite. So this is some kind of jarosite, similar structure or similar chemical properties. And if we are aiming at this is this is easiest part. So it can have high ferric ion concentration, and we can have high sulfate weight or acidic conditions, and temperature is quite low. So this is easy one, and we can easily precipitate iron in this with this formula, and no zinc will lost in this part. And another one is geosite. When we would like to precipitate iron with geosite, we have to control the ferric ion in the solution phase. So it should be less than 2 gram per liter, less than 4 gram per liter. And the preparation of geosite precipitation can be realized at ambient atmosphere, because the temperature is around 75 degrees C. And the third one will be the hematite. If we are aiming at preparing hematite precipitation, so we have to use autoclaves, because the temperature is higher than 100 degrees C, and also the ferric ion concentration should be well controlled. It should be low than 2 or than 1 gram per liter. And besides the temperature and the ferric ion, and also the acidity should be controlled. Because hematite is only stable with quite low acidic concentrations, and geosite as well. So if we are removing iron in the form of geosite or hematite, we have to make sure that the iron is in the right form, and the concentration of ferric ion is small, and also because of the link chain part has make a quite strong acidity of the solution phase. So the solution phase should be neutralized before we are using hematite or geoside process. So there are two sentences which made the remark. So ferric ion depends on the cementate phase, acidity, temperature, and solution composition. Jemicide method is widely used, and geoside and hematite are also used because it needs more critical requirements like the acidity, temperature, and ferric ion concentration. And as we mentioned, we can prepare ion precipitate in the form of hematite, geoside, or jemicide. So they are chemical formula of this precipitate like this, but the cyanotic content of iron is different. Just like if we are preparing hematite, 70% of this product is iron. But if we are preparing jarosite, only 30% to 35% is iron. It means that when we are moving same amount of iron from the solution, the solid waste production will be 2 times larger than hematite precipitation. And geoside has some middle numbers. And because of the formation complex system, the formation of hematite, geoside, or jemicide cannot get a single or pure product. It's always a mixture of different iron minerals or iron precipitates. So the actual or industrial sample has different iron content, but it has similar law. When we are preparing hematite, the product has highest iron content, and besides iron, the sulfur zinc content is also varied, and it has the lowest sulfur and zinc content. And geoside and jemicide has quite high sulfur content. And also have we mentioned, because we are preparing some iron precipitate from solution phase, so some amount of zinc sulfate cannot be washed. But when we are preparing this iron precipitate, we will think about whether we can use this precipitate in some other process, like can hematite precipitate can be used for iron and steel preparing. And this is the topic we talked with Becca in the first week. Because the iron content is more than 50%. So it can be used for iron production. But if we are preparing jemicide, the iron content is too low to be used for iron production. But for iron production, impurity elements like zinc, like sulfur, should be well monitored, because zinc, sulfur, they are sensitive or quite harmful impurity elements for iron and steel. So with some industrial practice accounting, we find out that when we are producing 1 ton zinc slab or zinc cathode, around 200 gram to 220 gram hematite precipitate will be produced. And if we are using this one, around 1 ton jarosite will be produced. So when we are taking the zinc hydrometallurgy industry in China as example, we'll find out that more than 1 million ton of zinc precipitate has been processed, and the number ranged from 1 million to 6 million ton per year, and has some sulfur, some acid. So majority or mainly those zinc solution, those ion removal precipitate are toxic or a toxic solid waste or hazardous solid waste. Hazardous solid waste. So when we are starting, those technologies step by step or one by one. So when we have some ferric ion in the solution, and when we are running or processing the solution at the processing window of jarosite, we'll find out that when we have some like sodium ions, sodium or potassium ions, they are secondary cations. When we have secondary cations, when we have ferric ions in the solution, and some acid is consumed, and we are producing this jarosite type precipitate, and also large amount of acid will form. So the ion removal process is also a process for acid generation. So after ion is removed, how to say, corresponding amount of acid will generate in this process. And when we are preparing some jarosite, the pH value is around 1.5 and temperature is around 90 to 98 in industry in order to get a better process, and better product. So aluminum ions and crystal seeds are also needed. And this is the picture. Actually, I finished this picture 15 years ago when I was an undergraduate student, and I was doing some ion removal experiments in the lab, and I have made an SEM picture for the jarosite. So the jarosite has quite a large particle size, and the solid and liquid separation process can realized in a short time. When we have a well process, a good process. But the problem is that the yield or the amount of jarosite is too large. And 1 ton zinc cathode, we are producing 1 ton jarosite residue. And another technology part is jarosite. We can also use jarosite for this part. And jarosite needs a controlling of ferric ions concentration. So it should be reduced first. We are using concentrate for reduction, and we are producing ferrous ion and elemental sulfur. And after that, when the ferric ion concentration is low enough, or when it reaches the criteria for the precipitation of jarosite, we are oxidizing this ferrous ion slowly, and the oxidation speed of ferrous ion equals to the precipitation of jarosite. And with this controlling step, we are producing jarosite precipitation. And easy is another one. We have 1 tank. We are pulling some solutions like contains some ferrous, and this is a clean tank with only some water and some zinc sulfate solution. When we are pulling this solution contains some amount of ferric ion, and we are making some how to say some blending or mixture. The adding speed of ferric ion equals to the settling speed or precipitation speed of jarosite of geosite, and we are making this easy process. And another one is hematite. So when we are using hematite process, the lateral lynching residue is processed with sulfur dioxide reductive lynching. So all the iron will transfer into ferrous iron, and we are injecting oxygen, and we are also controlling the speed and temperature. So with this speed, this zinc, this ferric iron will transfer into hematite, and the pH value was 4, and the hematite will have a better or more promising future. So this is hematite in the Ijima Agida zinc hematite process is quite nice controlled. So the sulfur dioxide is injected in the autoclave, and with some neutralization and clean gypsum is recycled, and with some zinc dust and the copper can be recycled in this slurry. And after that, oxygen and steam is injected and hematite precipitated in this process. So zinc hematite is a noble determination. But is a noble product for iron removal process. So after iron is removed, those solution contains quite high content of zinc and acid, and they can be recycled for returned for lynching purpose. And in this natural lynching process, the lynchant contains certain amount of zinc and certain amount of copper, cadmium, cobalt, antimony, even some hydrogen elements, and they are the raw material for purification and electrowinning. So in the purification process, we are recycling those valuable metals and get their solution prepared for electrical winning process. And when those impurities are high in the solution, we will have some problems with the cathode, unqualified. So deep purification, copper, cadmium, cobalt, nickel recovery should also be realized. And in the purification, very simple mechanism. So zinc powder is used to replace the other elements in the solution. So we are getting those products as how to say, as filtration cakes like copper and cadmium and cobalt. So this is purification, and there are some steps, some different technologies like arsenic assisted purification method. And this is one of the most important applications of arsenic nowadays. And arsenic in the form of arsenic trioxide that can be added into the purification process and will form intermetallic compounds and will lower down the reactivity of cobalt and can improve the recovery and of cobalt, and can also improve the purification process of the lateral lynching solution. And another one is antimony assisted purification method. It has similar story with the formation of intermetallic compound. It can improve the process. And in the last step, when the lateral lynching solution get purified and all the impurity elements are realize the limitations or realize the requirement, the solution can be used for electrolyte. And in the electrolyte chemical system will be, so the cathode is alumina, and the solution will be zinc sulfate and sulfate acid. The anode is made by lead with some amount of silver additives. So the cathode is rolling alumina and anode with some certain amount of silver, as I have mentioned. And we are controlling the acidity as well, around 2 more sulfuric acid, and the zinc content in the solution is around 1 more, and we get some amount of manganese in the solution. And in the anodic reactions, there are some main reaction will be the formation of oxygen, but because of the material of the anode, the oxidation of lead also happens. And besides the oxidation of iron, the magnesium oxide in the solution can also be oxidized, and there is formation of the anode slurry. In the cathode reaction, the soluble zinc cations deposit in the rolling alumina, and some secondary reactions like the formation of hydrogen and some precipitation of cobalt can also happen. But when we have the purification process well processed, and we can produce high quality zinc in the cathode. And there are some numbers of processing parameters of electrical winning process, like temperature and the current density and the current efficiency and the consumption of DC power, like 3,000, and the quality is around 99.99. So this is a industrial or well processed, a good process. This is the tank equipment. So this is the electrolyte cell, and this is anode. This is the cathode, and we have some rubber clippers at the edge. So this is a most widely used process for zinc production, and probably we will have some light discussion or questions after my presentation. I would like to finalize this part 3 first, opportunities and challenges in my mind about zinc production. And I have read some papers about at 2020, and was published by Danny Simpson and some researchers from Queensland University in 2020, and they have been explaining about the process of copper, lead, and zinc. They should be well designed, and they should process in a nice way, because as we mentioned in zinc today, there will be some residues like lead and silver leaching residue. They can be returned or sent to lead process, and we can recycle those lead and silver in this process. And in the lead process, there will be some minerals containing high amount of zinc. And in this process, there are some secondary zinc oxide. So the zinc oxide can be returned to zinc. And also in the precipitation or purification process of the electrolyte, there will be some copper content filtration cake, and they can be moved to this copper process. So these 3 metals are 3 very important base metals in non-ferrous industry, and their starting materials has very close relationship, and they are associated with each other. So they should be well designed. And this is my first thinking about this opportunity and challenges. And the second one is about the raw materials. So electrical arc furnace dust, which is high with iron, zinc, and hydrogen, and chloride hydrogen elements, and bottom ash when we are treating those municipal rubbish and or municipal waste. We will have some bottom ash. They will contain certain amount of zinc. So this should be the raw material for zinc production in the future. And actually, I have posted one picture in my slides. We finished 3 weeks ago. Actually, it's about a smelter very close to our campus, around 3 hours drive. So this is 3 smelters, like which is zinc, copper, and lead. As we mentioned in the previous one, copper, lead, and zinc should be well designed, and this is in one small district. So this is the zinc smelter, and the picture is taken somewhere here. And just opposite this street, there is a copper smelter. And 2 kilometers from here, there is SKS bottom below inlet smelter for zinc or for lead. So this is something is happening nowadays, and we hope we have a brighter, we have a more promising future for this zinc process, also for copper and lead, even some other non-ferrous metals. Okay, so this is my presentation for this afternoon, and I'm happy to get some comments or get some questions from you. Hello?
Okay, thank you very much, Longgong. Everyone, please ask question, and thank you for a nice lecture, Longgong. Sometimes
Thank you very much.
go Taufik Hidayat also take some slides from you as reference for his class of recycling. This is quite nice. Please, everyone, you can ask. You can raise your hand or type the question in the text.
Yes.
Don't be shy, okay? Okay, I have chocolate for the best question. Okay, because this is
So
very
Imam,
unique process. We don't, yeah. In Indonesia, we have recycle of lead, but using dangerous way, traditional way. They just burn behind their home people, and then it cause a lot of problem, health
do
problem.
you have some numbers about the yield of iron steel in Indonesia?
Sorry.
The production of iron steel in Indonesia. Do you have some
Yes, of
numbers?
course we have big Krakatau Posko. Yes, Posko. Yeah, and also
Okay,
in
so
Morowali, Chinese company, we have the iron and steel company.
so you must consume some amount of zinc. Do you have the idea about the number? Or do you have any idea
Yeah,
about
I don't have any idea. Okay, everyone, please ask question if you have a question for Dr. Longgong.
Masih watching, I want to ask a question.
Yes, yes.
Okay, thank you for the opportunity, Imam. I want to ask in roasting processes, especially in the Kellogg diagram, I believe. In industrial cases, okay, the point is fixed at point A and B. Yes, this slide, yes. I'm wondering, why are we engineering the temperature, not the partial gas pressure? Is it practically hard, or how is the mechanism? Because from what I have learned before, to control the temperature, we have to control the feed of the system. So I'm assuming that that process is easier than the controlling of the partial gas pressure. Is it true, Professor Longgong? Thank you.
Actually, you have raised a very good question. Usually, how to say, point A and point B refers to the gas composition about sulfur dioxide and oxygen remain oxygen in the gases. I would like to see point A and point B are taken from industrial practice, and the temperature can be easily or can be monitored or can be adjusted with a cooling system, because the roasting process has, how to say, has a lot of energy which should be cooled down with reverse or with some cooling water. And because of this X energy released during the oxidation reactions of the concentrate, so temperature controlling is not a big issue. And the gas composition, properly, I would like to see as more or less determined, or more or less a common practice in this process. So instead of changing the gas composition, the changing of temperature will be easier. And I have got some information. The temperature ranged from 900 degrees C to even 1000 degrees C. And the temperature is changing. It's getting higher and higher.
Is it okay, Nabil, answering your question?
Yeah, it is very clear now. That's very new knowledge for me that we have to use the cooling system. Thank you, Prof.
Any more question, guys? Some student already left before. Okay. It's
Sure.
12. Okay, anyone, any more questions? If not, let's thanks and applause to Dr. Longgong for nice presentations and see you again tomorrow, Longgong.
Sure. Thank you very much. And
Yeah, thank you
see you
very much
tomorrow.
and bye-bye, everyone.
Bye-bye.
Thank you, Longgong. Bye.
Bye,
Bye.
Pekka.
Bye-bye.